Welcome to the online causal inference seminar. Today, we're excited to have Susan Athey talk about synthetic differences and differences. Yeah, as I said before, if you have questions, please submit them in Q&A. Guido is with us today. He's a collaborator on this project and he's happy to answer all your questions. And we might also select some of them to be discussed in person. Questions today will be handled by Guillaume. So I'm switching over to him now.
Thank you, Dominic. As Dominic mentioned, we're going to do things slightly differently today. So Guido will be answering questions through the Q&A. We are also going to select questions and give you the opportunity to ask the questions live, time permitting. If your question is selected, I'll ask you to unmute yourself, or I will unmute you and promote you to panelists, so you have the opportunity to ask follow-up questions and kind of participate in a more interactive fashion. So this is a new format, so please forgive us if there are any hiccups. We'll get better. All right, Susan, whenever you're ready.
Great, thank you. Let me get my screen going and get everything organized in Zoom. Okay, thank you so much for having me here. And I actually want to give a really big shout out to Dominic and Guillaume and everyone else that's been working hard on this seminar. I really appreciate all the efforts that everyone has made to make this an interactive experience and to really innovate in our experience with this online seminar. So thanks so much for doing so much work on that. So today I'm going to be presenting synthetic difference and differences, and that the co-authors are listed here. Dmitry Arkelingzi, I always muddle his name, Skip Hirschberg, Hito Imbens, and Stefan Wager. And we're also going to touch on another paper that I have with another set of co-authors listed here, including Mohsen Bayati, Nick Dwachenko, and Hito and Kashar Khosrowsky. And we are, Hito is here, and actually recently he was giving a seminar and his laptop ran out of batteries. And so I had to pick up his seminar while he went and plugged it in and ad lib on the presentation. So I figure he owes me to answer questions today. And he'll be monitoring the Q&A as well. Okay, so we're motivated by the fact that there's a really very large literature on using this kind of panel data designs, longitudinal data designs to answer questions about policy. And just an example of the kind of question that these methods are intended to answer, we can consider California's anti-smoking legislation, Proposition 99. And there was a 25 cents per pack excise tax increase that took effect in 1989. And so the question would be, what was the causal effect of the legislation on smoking rates in California after that? And so when we think about what data we have to answer that question, of course, we can see the before and after in California, but we need to impute the counterfactual of what would have happened without the law. And so the real focus of this is imputing the counterfactual. The data we would have is again, the California data, but also other states before and other states after, and the other states didn't invoke the legislation. And of course, we may also have other variables, but those aren't of the essence. And so we're just going to abstract from observable covariates other than outcomes today, although those can be incorporated in various ways. So this type of study is, as I mentioned, just extremely, extremely popular, especially in like parts of economics where we're trying to study questions that would otherwise be relatively difficult to answer, especially questions that might affect kind of local economies. So, minimum wages, taxes, other like, gun legislation, access to health. There's many, many things that vary at the state level or maybe at the country level, sometimes at the county level, that we'd like to study where this type of data setup is available. And it's nice because in principle, it's going to allow us to do credible causal inference. And another nice thing, which I'll come back to, is that this type of setting is especially good for also evaluating the quality of your methods, because we do have a lot of units that never adopt a treatment at all. So we can do various types of placebo studies to see if our methods would have falsely found an effect in other states that that didn't actually make a change. And so one of the things I'm going to talk about today also is how to design really good quality simulation studies in this type of environment in order to evaluate methods. That's sort of from a contribution perspective, that's kind of it's not a theorem, it's an add-on, but it's something we spend a lot of time on. And we have some contributions to that relative to the kind of standard practice, particularly, recognizing that one of the things we really worry about in these kinds of studies is that somehow, California is different from other states, not just in one single characteristic, but California might have a different kind of time trend, and states that are doing badly might be most likely to adopt a legislation, or maybe states that are doing well are most likely to adopt this legislation. And so we really want to be sensitive to all of the different ways that the states that adopt might be different. Okay. So just to set up the kind of formal structure here, we're going to be thinking about a setting where there's a block assignment of the treatment. So in terms of outcomes, we're going to have an N by T matrix, and as units T is time, of realized outcomes. So we observe the realized outcomes for everybody. And then there's going to be a treatment matrix, and that is going to have block assignment so that there'll be zeros, everybody's control, except for a certain set of units after a certain time, they're all treated. And this is kind of a standard setup. In other papers, we look more at the setting of staggered adoption, where like different states are adopting at different times, and you kind of have a bit of a triangle of treatment assignments. So if several papers looking at that case, but today we're focused on, in most of the talk, we'll focus on the block assignment. The other paper on matrix completion looks more at staggered adoption. So here, the goal would be to estimate the average treatment effect for the treated units. And basically what that's going to boil down to is imputing potential outcomes for the states and time periods that were treated. So, and in the special case, we can have a single unit time period treated, and for exposition, that's going to be something that's especially easy to focus on. Because then we don't have to worry about averaging of these units. So one of the most popular methods of doing this, and something that's really gained popularity in the last 10 years or so as being really a leading approach, are the synthetic control methods introduced by Abadie-Diamond-Hainmueller. And these methods are not just, popular, they're also very easy to explain to policymakers or business leaders. So they're also popular and gaining popularity in firms and other places. And I've personally used these kinds of methods in a variety of settings with people who don't have a lot of statistics background, and you can just sort of show them what's going on. So just to start with like a picture, and just ignore the blue line in the picture for the moment, we'll come back to that later. In this picture, the purple line are smoking rates in California over time. And the green line is the weighted average of the outcomes of a selected set of other states. And I'll get to more details in a second. And so this is, like I would say, at first glance, a successful looking picture for synthetic controls, because what you've done is you've figured out weights on states other than California, such that when you draw this picture before the treatment, and the treatment is this vertical line here, before the treatment, California's trend is equal to a weighted average of those other states. And it's not just that it's equal at a point in time, but it's sort of tracking the time trend. And so this is where, like, if you show this to a business person or you show this to a policymaker, they're kind of like, I don't know what you did, but it looks good to me. You've actually, you've convinced me that whatever it is about these other states, that they seem to certainly be following a very similar trend. And then you see that California starts to head south, and that looks like visually very compelling evidence that this legislation worked well in California. And so here's a case where they're multiple years after the treatment. And so here we were looking at the average effect over a multi-year time period. So the green little circle is the average synthetic control prediction, the average of the weighted average of the control states over that time period. And then the purple dot the purple line is what actually happened. Okay, so I'll come back to the rest of that picture later. And so just in notation, what we can write down is what we're trying to do. And in now the notation, I'm going to the case where there's just a single time period and unit. We're trying to predict the counterfactual potential outcome if you were control, where we're averaging over the control states 1 to n-1. And what we're looking for are these weights, omega I, on those outcomes in the final period. And so how do we choose those weights? Well, we choose them so that in the periods prior to treatment, so all little t from 1 to t-1, for each of those little t's, we want the weighted average of the control states to be equal to the treatment state. And what that's typically done, the weights are typically constrained to be positive and to add up to 1. And that, again, it's not just for regularization, but it also can help a lot with explanation and intuition. So we can actually name the states. Here are the states that we took a weighted average of. Here are the weights on those states. And now it's very clear how you got your counterfactual. And the thing that makes this difficult is, of course, there's more than 1 year, and you only have enough weights as there are units. And so you would say this like visually looks successful when we found a smaller number of weights that's able to match the time trend over many periods. Now, there's an original kind of proposal for this method, and then there are many, many refinements and improvements about how to do this in various ways. But I would say that when the practitioners do this, a lot of times there's a bit of an eyeball element to it. So you have choices to make. You have to say, well, how many states are candidate synthetic controls? How many years do I try to match things up for? And, how do I exactly evaluate success? And so over time, people have figured out, ways to make that more systematic. One contribution of our paper is going to be to have a particular way to make it even more systematic and to systematize other elements of the analysis as well to make this work better and leave fewer choices in the hands of the researcher. So instead of kind of eyeballing and saying, well, should I go back to 1970? Should I go to 1980? We're going to use data to try to determine, how many years should be used, for example, for this exercise. Now, one of the extensions or elaborations of synthetic controls is this paper that by Hito and where they look at the synthetic control weights and view them as regression estimates. So as I mentioned before, here we're thinking of these as just like literally weights, and you're taking a simple average, but you can also view the synthetic control problem as basically what we call a vertical regression. And so vertical meaning that like I'm taking a row and regressing it on the other rows. I'm taking the row, which is the treated unit, and regressing it on the outcomes of the other units. And that's coming from like a matrix representation, that visualization of vertical regression. And so instead of just trying to solve a minimization problem that's about solving the minimization problem here that I illustrated with the constraints of the omegas positive and adding up to 1, instead we could, for example, do a regression or a regularized regression to find these weights. And the regularization may be especially important here if there's more units than time periods. And especially if you don't restrict the omegas to all be positive, then regularization, then you might need some other form of regularization. So they explore this regularized regression interpretation of how to come up with the weights. And we want to note here, this is a regression with T-1 observations. So there's a certain number of periods and N-1 regressors. That is, you're trying to, regress on the other units so that the weighted sum of the other units equals the treated unit. And so regularization may also be important depending on the relative sizes of T-1 and N-1. Now, one of the reasons we want to kind of talk about this in a regression framework, and we're calling it, vertical regression, is that it's clear that the units and time periods at some level are symmetric mathematically. There may be differences substantively, like might be worried about time series correlation in the outcomes, but we can also turn this problem around and look at it another way. So instead of sort of thinking of the treated unit and trying to express the treated unit as a weighted sum of other units, we could also take the final time period and think of it as a weighted sum of other time periods for each unit. And that would basically just be, transposing the matrix to get that interpretation. And so here, what we would be saying is, I would say this is an interpretation would be more commonly used when people take like unconfoundedness type approaches, typical cross-sectional causal inference approaches to the panel data setting. And so just what that would look like is now I'm trying to find weights such that for each unit I, the final time period is close to a time-weighted average of that unit's previous outcomes. And so this type of thing's naturally done, and people do this all the time also. If you're in a situation, maybe you only have 2 years of data, maybe you have 3 years of data, or you have a couple of weeks leading up to an intervention in a tech company. And then you can basically think for each unit, their previous outcomes are actually just control variables. They're pre-treatment variables. And we can think about this in the unconfoundedness setting where we want to argue that conditional on your pre-treatment variables, the treatment assignment is as good as random. And so I can try to flexibly control using whatever your favorite methods are, doubly robust methods, to control for the pre-treatment variables. And so there's this other literature that would do it that way. And they wouldn't really pause to think about it that much. They would just make the assumption and go forward using those things as covariates. And again, there's not that many choices if you just have 1 or 2 of them about what you do with the matrix. Now this horizontal regression, because now we're essentially regressing like the last row of the matrix, the last column of the matrix on the previous columns in the n/t format. We've got the number of observations is equal to n-1, the number of units, and there's capital T regressors, which is basically all the previous history. So this is what we're trying to do. Now, and I would say that one of the reasons we go slow in kind of presenting this way is we want to kind of emphasize that there's actually a fair bit of symmetry here between the synthetic controls and the horizontal regression. Those literatures hadn't connected that closely because a lot of times in whatever setting you're in, you had limited data in one form or another. So people often use synthetic controls when there's a small number of units and lots of time periods, and they use this unconfoundedness when there's a lot of units but not a lot of time periods. And so they don't spend a lot of time belaboring which one they should do. In a final one, which was super popular when I was a child as an academic, and remains popular for a variety of reasons in terms of sort of scalability and so on, is the case where you have you model a 2A fixed effects regression. So now we're going to just use outcome modeling. We're going to say the potential outcome is a function of a constant, a unit effect, a time effect, and an unobservable. And then we try to find the unit effects and the time effects. And then we put together the counterfactual based on those estimates. So we just get the unit effect for the treated unit, the time effect for the treated time period, and add those up to get the counterfactual. So this is also popular, and it can be useful like when there's other covariates, people treat it as a regression when there's time varying covariates, so it's like easily extensible in other ways. So then we've kind of come to, okay, how do we reconcile all these different approaches? And one way to think about, and they're all basically coming up with, just to say, they're different weighted averages, right? In this thing, the alpha hat N and the beta hat T are weighted averages of outcomes. They're particular weighted averages. In the horizontal regression, there's a weighted average of the lambda hat, but again, that lambda hat's also a function of the data. And then here in the vertical regression, we've got weighted averages across units, but again, the weights are a function of the data. So these are all different weighted averages, and we want to think about, what assumptions do they make, and which ones are appropriate in different settings, and how can we possibly get the best of both worlds. So the vertical or synthetic control regression is basically assuming there's a relationship between different units that's stable over time. The horizontal or unconfoundedness type regression assumes that there's a relationship between outcomes in the treated period and the pretreatment periods that's the same for all units. So it's saying, if things are going up, or if you have a certain weighted, if today is a certain weighted average of yesterday, that's stable across units. And the difference in difference regression assumes that there's an additive outcome model, and that with these just additive effects, we can capture all the time differences and the unit differences. And so the goal of our paper is going to be to, instead of trying to choose between them or compare them, to find methods that capture the benefits of all three. So here is, I think, a good place to maybe stop. I'm going to be, getting a bit more formal next. So let me pause here and take questions.
So there are a few questions that Guido is currently working on. So maybe we'll wait for the next stop until we've identified what are good questions to ask you. Okay. If that's okay.
Great. Wonderful. Okay. So now I'm going to go forward and I'm going to propose an outcome model. And I want to really slow down here and highlight, because there's going to be a disconnect where we're going to specify a data generating process that for most of the methods we consider is more general than any of the methods that we compare. So just to flag that, we're kind of just because I'm writing down the outcome model this way doesn't mean we're going to estimate it this way. So what we're going to assume is that the matrix of outcomes can be represented as the sum of another matrix L and tau, the treatment effect, times a matrix of treatment indicators. And so just writing it this way, of course, if without any restrictions, this is sort of useless because Y and L are the same size. And so the restrictions are going to come in that we're going to assume that L is a low rank matrix. And so those of you who are used to thinking about matrix factorization, this is, of course, very obvious if you're coming from a literature where you don't normally think about that. One way to put intuition into the assumption is that we're going to assume that for any observation for say, the ijth element, say unit I time j, it can be decomposed into, it's basically can be written as a dot product of two vectors. One vector is a unit vector, a unit latent vector, and the other vector, this mu j, would say be the time vector. And so one way to interpret this from in an application, if we were thinking about states, beta I could be a vector of states I's industry shares. So you could think each state, if our Y is economic output, we could think that different industries have different time trends. Beta I is the state's industry shares, and mu j could represent outcomes for each industry in time j. So if one industry is growing and another industry is shrinking in terms of output or in terms of economic activity, then we would be able to see that the state's overall economics would go, say, down if it's got a big share on an industry that's declining. In the smoking example, we might think about this as sort of the demography of the state. There might be different groups that are, more likely to smoke for cultural reasons, and so that would help us understand that. Now, the key assumption is that that's going to be stable, and of course, even in the examples I just gave, you can imagine that some of those things themselves would vary over time, which is one reason that this is a restrictive assumption. So that's basically saying that the outcomes have some structure to them, but not necessarily an additive structure. The second question is about formalizing our identification assumptions, or the assumptions under which we can actually, even if we had lots of data, get an unbiased estimate of the causal effect. And it's actually interesting that in this literature, there's not sort of uniformity about how people state these assumptions or how you should state these assumptions. But here, which assumptions you should make. And sometimes people make, assumptions that are sort of specific to the estimation technique they're using. Like they would make an unconfoundedness assumption in the example where you might say, as I mentioned earlier, if you're doing this unconfoundedness type thing, you would basically, the unconfoundedness assumption would basically be that these outcomes for a unit in previous time periods are the X's, the pretreatment variables, and you would be assuming that the treatment assignment was as good as random, conditional on those pretreatment variables. So here, because of the method you're using, it's kind of natural which assumption you should make. But if you step outside of the method, it's not as clear which assumptions you should make. So here, what we're going to assume is that this L is a latent matrix, and we're going to assume that the treatment assignment is not going to have to be independent of the L's. So we're going to allow that the treatment assignment can depend on these latent vectors. So it could be that there's some states that have higher industry shares of they have more steel, and we're going to allow the treatment assignment to vary according to how much steel they have, even if we haven't explicitly observed the industry share of steel. That would be a latent variable. So we're assuming that there's structure to the treatment assignment, but not that we explicitly observe the factors that drive that, but they're estimable. So our approach is going to be to allow the true DGP to take this form, but our estimator is not going to require estimating the true factor matrix L. Now you may ask, well, why don't you just estimate the true factor matrix? That seems like the obvious thing to do. And indeed, that is something that we work on in another paper and look at some of the specific issues that come up for causal inference in that. One of the things that's important here is that we're really trying to target something. We're interested in a counterfactual for a specific part of that matrix. And so whatever approach you use, you don't want it to just fit the matrix in general, like a standard prediction method would do, but you need it to be targeted to the counterfactual of interest. And that's why the answer isn't just as simple as just estimate the L. But then we're going to show that our methods actually do better than methods that just try to estimate the L as a result of that insight. So now let me show what our method is going to be. And so we're going to call this method synthetic difference in differences. And it's going to basically pull together a lot of the pieces I've just discussed. So what we're going to try to do is first construct a modified version of synthetic control weights. And what that's going to consist of is we're going to use penalized least squares to find a weighted average of control units that have a pretreatment parallel trend to the treated unit average. And I should say parallel trends is the term that the applied literature uses. What all we really mean is just that we want to fit in every period. And so when you draw a picture, it looks like a trend, and so we'll fit the trend. But just from the programming perspective, we just want to fit in every period. There's nothing more to it than that. Trend is sort of an extraneous word. So here what we do is we think about the weights we use for the units as solving this minimization problem. There's going to be a few differences from synthetic controls. First of all, instead of the regularization of having them all at instead of the regularization before, we've got them basically using a ridge regression penalty. And so what we're going to do is try to minimize this regression, this loss function. And one of the other changes from synthetic controls, which seems very minor, but it's very important, is that we are also going to allow a constant term. And so in the traditional way of looking for these weights, we're just looking for each state to be a weighted average of other states, which basically means this is going to work well when your state of interest lies in the convex hull of the other states so that you can actually find the weighted average. But if they're shifted up or down, that's a problem for this traditional synthetic control method. While here we're allowing that to happen. And so here for the time weights, we're going to do the same thing. Now, in most cases, we're treating things symmetrically, but here we're going to be a little bit asymmetric. We're not going to actually regularize the time weights. And while in principle, you can apply our method reversing the roles of units and time, one reason we do it this way is that while the units may be sort of exchangeable, the time units may not be. And so we do want to allow our method to load up on recent units, recent time periods, and actually zero out longer ago time periods. And so if we use something like a ridge type regression, we would sort of spread out our weights over lots of time periods. And we're going to allow this we're going to allow it to kind of load up more on more recent time periods. So here we're going to have regularization on the non-negativity constraints and the adding up constraints rather than on penalization. Now, this is, I think, a little bit of an open question of I would say we've got a lot of stuff systematized. This particular decision and exactly how it works might be more or less appropriate in a particular example. So this part is a little bit ad hoc to just not have any penalization at all. I'll just leave that as something that could be further explored. We explored it quite a bit in terms of performance in the applications we were interested in, but it's something to think about. Okay, so now we can write down our method. And so for this 2x2 matrix is partly designed for the part of the literature that thinks about difference and differences in terms of there's before, after, and then treated control. And then you take the treatment effect is basically is forming the counterfactual from the difference and difference in this matrix, and then we compare that to the average of the actuals. And so here we're going to sort of modify, and typically if you did it that way, you would have sort of simple averages in these boxes, and then synthetic control or unconfoundedness would incorporate different weights. In our method, we have two sets of weights, unit weights and time weights, and so we can see how they play out here. So essentially, we're going to start with this first box here. We've got synthetic control is that those are our control units. And so instead of just taking a simple average of all control units or a weighted average using the omegas, our synthetic pretreatment average outcome is going to be a weighted average of similar units and similar time periods for the treatment units and time periods. So it's not just similar units, but now it's also similar time periods, and those might be more recent time periods. And we can think about the difference between the post-treatment and pre-treatment outcomes for the control units as the difference between the upper right box and the upper left box. In the upper right box, if there's just one post-treatment period, there's no averaging over time. If there are many post-treatment periods, then we take a simple average over time. And then we're weighting across units. So we can say what happened for the synthetic control group over time, it's the difference between the top right and the top left. Well, if we now go down to the treatment units, The after is just a simple average of units in time of their outcomes, and the previous time period for those units, we take the simple weighted average of the most recent or most similar time periods. So if there's just one time period and one treated unit, this just boils down to, you know, the treated unit in the last time period minus the treated unit, the weighted average of that treated unit in similar time periods or most recent time periods as weighted by this, this lambda t. And so difference in difference uses equal weights. Synthetic control takes only one difference and uses, basically uses 0 time weights. And so we've got this, we're treating the problem more symmetrically, and we have these different weights. So so just to kind of pull all this together, synthetic controls is usually not written this way, but this we did with a little algebra. Actually, we found it quite useful to rewrite synthetic controls as solving the following problem. We can take the synthetic control approach, which I've already explained, and rewrite it as solving a regression problem, where we're trying to, we have a kind of a fixed effect for time. And we're weighting units using synthetic control weights, and then basically just, you know, regressing, we're regressing outcomes on time effects and a treatment dummy. And that's going to give you exactly the synthetic control estimate. And then that's when you write it this way, you see, gosh, that's kind of funny because you've got a time effect, but you don't have a unit effect. And so the time and unit are treated asymmetrically. The difference in difference is unweighted, but it has unit and time fixed effects, while the synthetic difference in difference is a weighted regressing with unit and time fixed effects. And so this is how we're pulling them all together. Okay, should I stop and take questions now, or we have another stopping point in 3 slides? Are there any questions?
Yeah, actually, so there's a question by Grant, which who I'm going to unmute. So Grant, I think you should be unmuted now.
Yep, can you hear me?
Yes.
Yeah. Okay, great. No, my question is just about if you could talk for a second about the barriers to extending this to a heterogeneous treatment effect situation like the causal forest.
That's a great question. That's something I've thought some about. I think at some level you can augment. I think there's sort of just 2 things going on at the same time. So the simplest way to do this would be to think about like constructing a counterfactual and then trying to project the difference between actual and counterfactual onto X's in sort of a 2-stage fashion. But I think there's some disadvantages of doing that, not in very large samples, but in moderate samples. And so I worry about a lot about sort of trying to make sure you're comparing apples to apples and not sort of essentially looking at what X's, using X's to find like prediction errors that are spurious rather than you know, true heterogeneity. So I would say the open question that from my perspective is how to, I can see lots of ways to find heterogeneity in the strong signal case where you have pretty accurate models. In the weak signal case, which is the typical case where actually you're mostly noise and only a little bit of signal, I worry about finding spurious effects here and what are the best ways to avoid spurious effects. But this is something I've been interested a lot in applications, and I wish I had 3 papers about that topic already, but not yet. So I think the other very simple way to do it is to say, let's go back to the unconfoundedness setting. If you don't have a lot of pretreatments, then just, you know, think about the pretreatment variables as, you know, covariates, and then throw in, you know, more covariates. But you would have to be very careful about how to do that, and be also very careful about your unconfoundedness assumption and making sure you don't regularize away things you need to be controlling for. So bottom line is, at some level, it shouldn't be that hard in large data sets, but I'm quite concerned about it going long in small data sets or with lots of noise.
Hi, Susan. I have a question. So Can you hear me?
Yes.
Yeah, so here the time weights and the user weights are, the unit weights are estimated kind of separately. So can we do it in a more interactive fashion? For example, once we have information on time weights, can we go back and estimate user weights using the information on time weights, like a reweighted version? And once we estimate this user weights, again, use this information to come back and re-estimate time weights. So I'm like, my intuition says this may help in situations when we have a lot of users and very few time periods, or vice versa, the other way. So like, to me, this is like a one step of a more sophisticated model, or an approximation to a more sophisticated model. And yeah, like, any opinion or views in this direction?
Yes. So Hito, do you want to, I would say, I
Sure.
mean, every single one of these things are things that we've argued about at length. So let me let Hito summarize the arguments.
Yeah, that's a very interesting question. So clearly, at some level, it doesn't seem optimal to separately estimate the unit weights and the time weights, but it's very hard to find a way of systematically choosing them jointly, and to avoid ending up in a situation where you're just looking for a couple of periods and a couple of new units where the outcome is the same for all those units in all those periods. And so it's not quite clear whether there's a good criterion that would allow you to do this jointly. And certainly you can do it iteratively once or twice, and that may improve things a little bit, but it's not clear to me that you can gain much systematically. But if that was the case, then it would be most likely to be in the case where you have a lot of units and a lot of time periods. Because at the moment it's clear that having the units balance things in all time periods is going to be wasteful if you only really care about some of the time periods and the other way around. So I think there's something to be done there, but we haven't figured out how to make that actually work.
And so let me just say something about our philosophy there is that this is not like a theory paper for theory's sake. Like a lot of people are using these methods in a lot of fields. And so we took a fairly conservative approach of only, suggesting things that were sort of very robust. And worked across a wide range of applications and so on. So a lot of these things are, they're very natural directions to consider, but there's a big tension in the more tuning parameters you have, the more degrees of freedom. And remember, these types of methods, these are the ones that are coming out and people are using them about abortion laws and gun laws and, the impact of BLM protests in the summer on COVID. These methods are being used for very salient and important topics. And so there's an advantage to an applied researcher of using a method that doesn't have too many tuning parameters, because even the best intentioned researcher, they can have the results flipped if somebody changes a tuning parameter somewhere and then they get accused of problems. So, there's some tension here between complexity and kind of the most natural general model.
The other thing is that kind of since Alberto Abadie has introduced these methods, there's just a huge amount of theoretical work going on. A lot of the questions are kind of reflecting the issues where there's just no consensus in the literature exactly how to deal with them. But there'll be a lot more work happening on this in the next couple of years. It's just a very active area.
Yeah. So we absolutely encourage people to further explore those. It's just like in these things where it kind of maybe it depends, that might be better fleshed out in another paper. Okay. So let me then move ahead. So when we think about some of the properties of the estimator, one of the things that motivated us to think about it this way is that all of us have been working in the traditional cross-sectional setting where we think about unconfoundedness and there's beautiful double robust properties. And of course, there's, thinking about how important those can be both for theoretical reasons and for practical reasons. So we actually, this method here can be thought of as a double robust method because we're combining outcome modeling and weighting. So just coming back to look at this, we have these weights. We can think of this as a weighted regression. It's just a local linear regression with fixed effects for time and unit. And that, and of course, if you have good weights, then it won't matter very much whether you get the outcome model wrong. And if you have a good outcome model wrong, right? If you have a good outcome model, it won't matter so much what your weights are. And so that is in other problems that has been very important theoretically and in practice, and that is also what we find here. And so what we're going to show is that if the data generating process is a factor model, so just going back, here we've estimated a simple model. The true model is richer. So we're saying even if we're misspecified in our outcome model, we're only estimating fixed effects, but the true data generating process actually is a latent factor model, we still are consistent. And so that's nice because, of course, in practice, you might want to estimate a factor model, but you're not going to get your factor model exactly right. And so this is sort of allowing you to be misspecified basically in the factor model, which will be the traditional case. I mean, yeah, in principle, with large data sets, that's not as much of a problem, but in practice it will be. And even with bad weights, the SDID would be consistent if the things are fairly additive. And so it's going to that's going to give it sort of good bias properties and good theoretical properties in general. We can also, though, compare it to the matrix completion estimator, where you do actually estimate the latent factor model. We have this other paper where we talk about, there's many different ways you can estimate latent factor models. In this other paper, we talk about how nuclear norm minimization, which is basically like a matrix version of lasso, where you penalize the absolute value of the singular values and basically zero out singular values, just like you would zero out coefficients in a linear lasso regression. Is a very good choice for this case. And we also talk in that paper about how you should use inverse propensity weighting or something else to try to choose models that target the units most likely to be treated, but units and time periods. And so we're going to also compare this to the most standard version of this in our results. So pulling all of this together, here are all the different methods. Again, we've got, we're going to be taking different weighted averages. There's a table here. I kind of went through this slowly before, so I'm not going to go through it in detail now, but I could just say, again, we can think about the different methods as different weights we use to take weighted averages of units and time periods. I'll throw in a few more at the bottom. Matching, you would be weighting the closest control by one and not weighting anybody else. In propensity score, we might be deriving a propensity score and using inverse propensity weighting, and we could also think about double robust estimation in the kind of cross-sectional view of the data. So now I'll talk quickly about the properties of the estimator. We basically want to show asymptotic normality. The key insight is that the estimated weights converge to deterministic oracle weights, these pseudo-true weights, and then we establish all the properties we need with the oracle weights. The SDID has good and easy to understand properties, and then we decompose the proof that way. We basically have to show these steps. The estimated weights converge to the oracle weights. The estimator with the oracle weights predicts counterfactual outcomes accurately, and that the estimator with the oracle weights satisfies the central limit theorem around its expectation. So I'm actually not going to go through the details of the proof today. I think in an online seminar that's harder to do, so I'll refer you to our paper for the details of that. Let me just yeah, go ahead.
Sorry to interrupt. You have around 10 minutes left. This is not a hard constraint, but just to give you a heads up.
Okay, great. Thank you. Yes. So let me state the theorem. Basically, we get asymptotic normality for this estimator, and we can do inference by resampling the units. And so here's the expression. The assumptions, let me just go through the assumptions that we need because those are important. First of all, we're going to be taking averages over the treated units in the treated time periods. So we need either the number of treated units or treated time periods to be large, but they need to be small relative to the size of the control unit, control time period matrix. So when we think about doing the asymptotics, we think about sort of a matrix that's growing, but the treated block is going to always be small relative to the controls. The second thing that's really important is that while we said we can have a misspecified outcome model, it's going to be important that it's not, there is some structure in the matrix. If there's not enough structure in the matrix, then we won't be able to, we won't be able to control the properties of the estimator. And so it has to be small relative to the minimum of N0 and T0. So, and that's, of course, if we have rectangles of various shapes, we take the minimum, the skinniest part of the rectangle, and the rank of the matrix needs to be smaller than that. And so, again, that's going, even though we're not estimating L, we still are going to need to have the complex, we need to have enough data relative to the complexity of the outcome model that we're going to do a good enough job finding our weights. And so that's that the L also has to be well behaved so that this model fits well using oracle weights, and that the oracle weights need to be sufficiently spread out over units and time. And so again, we want to have enough structure in this that we're able to create averages where the weights are not sort of just concentrating on one similar unit and one similar time period, so that we'll actually be averaging lots of units, and the average is diminishing in variance as the matrix grows. And then finally, we're going to assume that the units are exchangeable, and the errors are Gaussian or similar. And we're going to assume there's not strong long-range dependence, which is just basically, again, saying that we can kind of understand the relation. There's enough information in the data, there's enough structure so that we can learn about the underlying outcome model. Okay, so those are the key assumptions that are required to make this proof work. So now I want to spend some time on simulations. And as I mentioned, actually, this is a great, if you're teaching or whatever else, like panel data sets are really great for doing simulations on causal inference, because you can do these placebo tests where you can say, here's a bunch of outcomes. You can download any matrix, even where there is no experiment or anything else. You can just download census data or any other government data that's got units and time periods, and say, hey guys, imagine that, do a simulation where you imagine different units were treated, and then see if you can accurately detect that there's no treatment effect in those units and time periods. And so that's a really nice way to validate estimators. And it's also, you can use similar ideas to think about doing confidence intervals as well. And so we can evaluate the bias and mean squared error of estimates as compared to observed outcomes. But the problem is that when you do that, it's typical to just say, okay, well, I'm going to imagine that whichever units are treated are random, and I'll just keep resampling which units are random. But that can be misleading, because if you're taking a random sample of units to be treated, then overall, the average of that random sample will be within the convex hull of the other units. And so in general, we're going to be unlikely to draw a set of treated units that are sort of systematically similar to one another and systematically different from the other units. So they can sort of overstate the ability of these estimators to work, because they're kind of averaging away the interesting case. And ideally, the simulation should be realistic, where the outcome model is tied to the actual data, and the assignment process is tied to regularities and the assignments of actual treatments. And so we found that this was very important in our simulations. And of course, there's a question of how to do this. So here we're proposing a way to do it that we hope other people may pick up on or improve upon in doing simulations in the future. And again, this whole thing would be a nice exercise for teaching, I think, because it also makes students think about data generating processes, which is always a challenge to get them out of the math and into thinking about the way the data came about. So we're going to follow this very, very famous, highly cited paper by Bertrand, Duflo, Mullainathan that looked at some issues around difference estimators. And they used CPS earnings data. This is just government available data. You can download it. They're for 40 years in 50 states. We're going to calculate average earnings from this government data. So that's going to be like the state level average earnings. And so our matrix is going to be 40 by 50 with average earnings by state. And then we normalize it by subtracting the mean and dividing by the standard deviation. Next, now that we have this normalized matrix, we fit a rank 4 factor model to that matrix. And so then we're going to extract a 2A fixed effect matrix from there that's based on unit and time effects. So basically, we're going to say the outcome model is unit effects, time effects, plus this low rank matrix approximation of factors. So F are the fixed effects. And so the residuals are going to form a rank 4 factor model, which we fit with an AR2 model. And so we're also going to, in our simulations, use that fitted epsilon model to generate the errors in our simulations. And so what we find in this particular setting is that the fixed effects explain most of the variation in the data. After the fixed effects, there's very little autocorrelation left in this particular data set. For the simulation design, we're going to create this realistic treatment assignment models. Now, remember, this is a case where in many applications, you don't have covariates or you don't have very rich covariates. And so we're going to be wanting, even without covariates, we want a realistic assignment model. And so we want the treatments to be independent of the unsystematic component of outcomes, but related to the time trends or the outcome levels for the treated units. So what we do is we start with a bunch of actual regulations, and we just pick some that have commonly studied, high minimum, and separately analyze each of them. High state minimum wage laws, gun laws, and abortion laws. For each of these 3 sets of actual regulations, we run a logistic regression to predict the presence of a regulation on the factors that were extracted from our estimates. Okay, so for each state, we've got state factors, and then we're going to regress regulation on those factors. And we show that actually in practice, the treatment assignment does strongly respond to these unobserved latent factors that we've estimated. So we estimated the latent factors, and then we see how much of the adoption is actually explained by the latent factors we estimate. And it's very high. It's R squared of 0.3 for minimum wage laws and also for abortion laws. So that is, there's systematic elements of states that predict adoption and that are also related to their latent time trends. And we assign treatments to states with probabilities based on the logistic model with a maximum of 10 treatment states. So this is our simulation design, and again, you can do this. We also try it with some other data sets and some other types of like international data, country data, and other types of treatments. But this whole thing can be done with public data, and it can be you can do this to try to assess how well the methods work in a case where there's some kind of endogeneity or confounding based on latent factors. And so now we compare the different methods. So the top thing is in our main settings. We try 2 different shapes of the treatment method of the treated matrix, whether there's 1 treated unit in 10 periods or 10 treated units in 1 period. And then we have 3 different treatment assignment models we consider, corresponding, again, to these 3 different logistic regressions we estimated. So in one, the treatments were assigned using the latent factors that were predictive of minimum wage laws. In one, they were assigned using latent factors that were predictive of gun laws, and one using latent factors that were consistent with adoption of abortion laws. And so what we find is that across the board in all of these cases, the SDID method does better in terms of mean squared error, except for this one case where the matrix completion does equally well. And so those are the base cases. Of course, this is our method in our paper, so of course we do well. But we want to try to show the conditions under which there's an advantage of our method. So the next set of things under constrained assignment says, what would have happened if we'd run these same simulations, except instead of assigning systematically according to latent factors, we instead did random assignment in our simulations. And then it would look like synthetic controls would do well. And part of the reason for that is that here one of the benefits of our method is that we're allowing for unit fixed effects, which allows us to use more units to be part of the synthetic control, even if they're shifted up or down from the treatment state. And if you're taking random set of states, that there's no benefit to that. And so then the synthetic control is sort of a more constrained model and gives less mean squared error. We also look at differences in the outcome models. So we look at a model where we generate the data pulling out the fixed effects and saying that there are no fixed effects. Everybody has the same mean and all the time periods have the same mean. And then also the synthetic controls do better. When we shut down the low rank factor model so that the DID model is well specified, we find that the DID model does best. And when we get rid of the noise, our model does well again. But we'll notice that even in in most of the cases where the other ones do better, we're still doing reasonably well. So that's sort of our saying. We're trying to get the best of both worlds. Of course, there's a cost of generality, and if it's totally not needed and you have a better specified model, you'll do better. But we're doing well in a richer set of circumstances. We also look at the bias, and our double robustness controls bias, and we have some good results on bias. I'll just close up by looking at going back to the original JAZA paper on California smoking and see how these different things look. So just visually, here's the treated units. In SDID, we are taking a weighted average of control units, but we're allowing them to be shifted up by a constant. And so the parallel trends, we're not requiring things to line up exactly when we take weighted averages. We can allow them to differ by a constant, which allows us to put weight on more units. And then these little blue things at the bottom here, this little zigzag, that's showing the weights, and it's showing that we're putting most of the weight on recent time periods. And so then you can just see if you actually get rid of that fixed effect, then we're lying right on top of the synthetic controls. So this says, oh, we really do have parallel trends. And this is just a visualization taking out the fixed effect for the units. Another thing you see here is that we're matching really well when it's close to the treated time period because we're weighting the treated time period. And out here, we're matching well in the out years, even though actually they didn't enter the objective function because we only weighted the recent years when trying to pick so when we're constructing this. Now, when we put in the synthetic control, it also looked good. But you can see that it doesn't fit as well in the years just before the treatment, and that's because it was trying to fit across a wider time period. Now, it looks pretty good, so you might have stuck with this by the eyeball method, but actually what our method says is it looks like, the synthetic, the control states were already kind of shifting down before the treatment. And so our method is showing sort of a steeper counterfactual decline than the synthetic control method, being more sensitive to the fact that that's what was happening right before the control. And then just zooming in on that, you can sort of see the differences between our two methods in the local time period right around the law change. And I would say just from a conceptual perspective, since this law should probably have effects over time, it takes time for people to quit smoking and respond to the tax. The fact that ours are kind of like fanning out over time, but there's not that much effect early on also seems compelling. So we look in the paper, we show how, we put more weights on more states, which also reduces variance. And we also show that, we are only putting weights on the last 3 years. So in conclusion, we think this is a natural and easy alternative to difference in difference and synthetic control. And we want to say when you're making those comparisons, you should use realistic simulations, but completely random assignment to treatments can be misleading about your choice of methods. But we're very excited about this whole literature. We're also excited so many people are working in this literature. And, I didn't have time to talk about all the great work that's going on in all the different directions. It's a great fun to be part of this really active literature. So thanks, and I'll stop there and take more questions. And Hito will help out too. I guess we're going to do the panel discussion, and Hito will help out with answering the questions from that.
Yeah, thanks for the fantastic talk, Susan. Yeah, we're kind of out of time, but I think if there are a couple of short questions from the panel, we can still take them. Just unmute yourself if you have one.
Kathleen here. Hi, Susan. Thanks for a great talk. I was just wondering what the simulation results look like when the T0 and the N0 are smaller. I couldn't tell from the simulation table what the pretreatment time period and number of controls were.
So Hito, are you taking that, or? You're muted, Hito.
So in the paper, there are results also for the case where we vary the T1 and M1. So we're allowing for the very short post-treatment periods and very few treated units. And there, the ranking of the different estimators still holds up. We're asking about short pre-treatment periods of the. So there, I don't think we did some simulations, and it again, things seem to be relatively robust to that. But exactly how short you can make that is not quite clear. So at that point, because if you have very few pre-treatment periods, the time weights are not going to matter very much anymore, because you basically reduce to using all the time periods. If you have very few, but if you have very few pre-treatment periods, you're going to have a hard time getting the unit weights right. So you may rely more on the regularization there to make that work. So I don't think for that case our method has any particular advantage relative to the other methods compared to the case where both T0 and N0 are relatively large, but I would expect the relative rankings to still be similar.
And so then our other paper on matrix completion, we actually do a lot of simulations changing the shapes of the matrices to kind of show that, you know, similar to what Hito said, like it's the kind of case where things are not too narrow, not too skinny, and not too wide, and not too skinny in one direction or the other, where there's room for alternative methods to start to help.
All right, great. Any further questions? All right, then I think it's slowly time to wrap up. So first, thank you so much, Susan, for a great talk. Also, thank you, Hito, for rocking Q&A. I think 15 answered question is pretty close, or the new record. Next time, we're going to have Mark van der Laan from UC Berkeley, who will talk about higher order targeted maximum likelihood estimation. We're looking forward to the talk, and we hope you all stay safe until then. Thank you all for joining, and hope to see you next time. Thank you.
Thanks.